we can get started. So welcome everyone to our colloquium today. And today we're very happy to have Anatoli Fedynitch, who is an assistant research fellow in the Institute of Physics in our academia syndicat. And so Anatoli got his PhD from CERN in Geneva and also KIT in Germany back in 2015. And after that, he held a few postdoc positions. First one in DESY in Germany, and then University of Alberta in Canada. After that, he was in the Institute of Cosmic Ray Research, ICR, in the University of Tokyo in Japan. And since 2021, he moved to Taiwan and started as an assistant research fellow in the Institute of Physics in the academia syndicat. So today, Anatoli will tell us about high-energy cosmic rays. Let's welcome him.
Thank you very much for the opportunity to talk. I'm also very surprised to see so many young faces at IAA compared to IOP's colloquia. This is, I think, a 500-fold increase. So, today my talk is going to focus on ultra-high-energy cosmic rays, and I will spend a significant fraction of bringing you the latest news from our main event called ICRC, the International Cosmic Ray Conference that concluded a few weeks ago. So I will talk about mostly data, and then I will spend time talking about the challenges, and then finalize with the opportunities that we have. So to talk about cosmic rays in general, I would like to start very, very generic. And cosmic rays are part of what we would call normal matter. And so these are everything from electrons, protons, and nuclei, so simply charged particles in space. And neutrinos are also connected to cosmic rays because some fraction of these neutrinos comes from cosmic ray interactions with gas. And cosmic rays should be of very high importance for astrophysics, since the energy density is comparable to most other sources of energy density in the universe. And and so I would like to emphasize that the study of cosmic rays at all energies should be taken very seriously and rigorously. So to give you an imagination what this general problem in cosmic rays is the shear scale. So here on the y-axis is unit 10 to the 4, or particles per some unit area, unit angle. And here at the bottom is 10 to the minus 28. So these are 32 orders of magnitude. And while at these lower energies connected to this is GeV cosmic rays, mostly galactic or solar cosmic rays, the rate is something like 1 particle per square meter per second. Already here, the feature we call Ni, the rate drops to 1 particle per square meter per year, whereas at this tip of the spectrum, it's only 1 particle per square kilometer per century. So just the appearance, just the sheer order of magnitudes engraved in the spectrum tells us that cosmic rays must have multiple origins. There cannot be one source here sitting here and there. So what does this ultra energy imply for the accelerators? And there is this famous Hiller's plot, and the Hiller's plot essentially draws the size of the accelerator region in centimeters versus the magnetic field, because in stochastic acceleration, you need to confine the particle for multiple turns, which gives you, by the Lama radius, a limit on the maximum energy the particle can have to be confined to experience stochastic acceleration. And there are a number of sources that are potentially capable to accelerate cosmic rays, starting from neutron stars, but also AGNs, jetted AGNs, GRBs, and all the most high energy violent objects, including also objects at very large scale, like IgM shocks in the galactic medium. The second thing that we have to keep in mind is if you would try to build an accelerator on Earth that would accelerate particles to the energies observed in nature, it would need to be of the size of the Mercury's orbit using the technology deployed at the NHC. So it's way beyond man-made capability to accelerate particle to these energies, which also implies, which also implies that even the physics that happens at the collisions of such energies is largely unknown. Okay? So this is a great opportunity to also feed back to particle physicists, some of whom think that cosmic rays might be not connected to traditional acceleration, but could be rather the imprint of all kinds of weird and exotic physics of particles at very high masses that would decay and fragment into other particles that we observe as cosmic rays. So all of these things, just implied by the number of the energy that is observed. So once we multiply the spectrum by the power of e to the 2.6, there's a random choice just to visualize the features. We start seeing different features in the spectrum. Okay? And this is mainly a phenomenological fit to all kinds of data that we have. Here it would be too messy to display the data points because the errors are quite large. And what we see here is that at these energies, the measurements are very, very precise. So this is due to the spectrometers used at energies like AMS or CREAM that are used to determine the charges of the elements. However, at high energies, this is already not possible. So to measure the spectrum in its entire shape, one needs different detection technologies, direct detection, and extensive air shower indirect detection, which I will talk a bit more about this. So all particles starting roughly from here, like EV and above, we call ultra-energy cosmic rays. So I focus on this part, and in fact, this is not, it's just like I ended up being interested in this, but there are also more features at low energies that we don't have very clear explanations for. There is no unambiguous explanation. So cosmic rays, even at other energies, are also kind of mysterious. So how do we know about that? And today there are mainly two observatories. One is called Telescope Array, located in the northern hemisphere in Utah. It's about 680 square kilometers in size. And the elephant in the room is the Pierre Auger Observatory, which is much larger, 3,000 square kilometers. And since they are on two hemispheres, they cover a different declination range. And here you can see the exposure that, this is Pierre Auger, and this one is the telescope array exposure. However, it is very important to have this detector because it covers the northern sky, which is invisible from the south, as astronomers obviously know. So we need both to have a full sky coverage. So how do these detectors look like and how do they work? So in principle, when a cosmic ray interacts with the atmosphere, it breaks up and starts creating secondaries, and the secondaries fragment into further secondaries. And so these big cascades, which are called extensive air showers, are created by the particle, and then at some point they hit the ground. And so this Pierre Auger Observatory consists of these white dots. So these are so-called surface detectors. They are water tanks like this, okay? And so the water tanks, so once a charged particle passes through it, it emits Cherenkov light, and there are PMTs that collect the Cherenkov light that's reflected off the walls, and they record the time traces of the photons by this charged particles. So to give you just an imagination, this is 70 kilometers. This is like from here to, I don't know, Miaolin maybe? Yeah. So it's a gigantic distance. So the distance between each of these tanks is 1.5 kilometers. Yeah. It's gigantic in size. And these other features drawn, these are fluorescence detectors. So the fluorescence detector is mainly a mirror and a camera, and they pick up the fluorescence light created by the nitrogen in the air if it gets ionized by the secondary particles passing through it, so they can record a time trace or a photon trace from the air shower hitting the detector. The other detector, telescope array, essentially works in the same way. Instead of water tanks, there are these great weird kind of devices that are completely autonomous as well as in Auger. And they have two scintillator panels recording the transition of charged particles, and there are two to actually reject random background. And they also have stations with fluorescence detectors like that. And it's not as closed as the Pierre Auger Observatory. Originally, TA was just this patch, yeah, with different here FDs, Black Rock, Milgram, Long Ridge. So these are fluorescence detectors pointing towards the inside. And recently, TA is expanding to TA times 4, so trying to increase the exposure by 4 times, building this array and that array with additional fluorescence and surface detectors with a larger density. So people want to have a slightly different science focus. So the detection is difficult because it's indirect detection. And so indirect detection, the more channels you combine, the better the more certain you become that your measurement is accurate. And one of the most certain things that you believe is certain is when an air shower enters the atmosphere, creates, so this is like the photon emission profile in fluorescence, and this is the depth, the standard, the grammage along the direction. So, and if the fluorescence detectors can record this curve, okay? So this is real data actually of an air shower, and then it follows some kind of specific distribution. What always happens as well is that the showers hit the ground, okay? And once they hit the ground, they're recorded by the surface detectors, the charged particle transition, so they leave an imprint, and this is how it would look like. So at some distance from the shower core, we can record signal in the tanks, and the signal has an additional sometime structure. So sometimes muons and electrons or late-coming particles look different. And so depending on the radius from the shower core, one can draw such kind of lateral distributions. And recently, in the last 10 years, radio detection became an additional option. So people like Auger in particular, they upgrade their detectors to put here surface scintillator detectors and radio on top. So they want like multi-hybrid detection that we really are certain about the systematic uncertainty. So how is the energy, if one uses the tanks and not the fluorescence pattern, how does the energy calibration perform? So here on the x-axis you have the energy measured by the FD, which is calorimetric. Yeah? You just integrate this profile and then you get a real good estimate of the energy. So this is here, and then on the y-axis there's a different estimator for the energy, and this is the observed proportionality. And you see at high energies it's pretty good, at low energies it's less precise. So you would draw this here, like the energy resolution is about 20% at 1 eV, but at high energies this becomes really, really good. Okay, so this is like 6-7% is the energy resolution of surface detectors. So these energies, in principle, we wouldn't need any fluorescence anymore. And another certainty why this reconstructing the energy works pretty well these days is this. So these are 5 different techniques, indirect techniques to measure the energy of each shower, and they are plotted here on top without additional systematic shifts, and they agree by default pretty well. Okay. So I think at least the Auger collaboration is quite certain that the determination of the spectrum is precise. And this is what they show us today. I mean, like 2 weeks ago. So this is the most recent measurement after 15 years of data taking. And the arrow bars here are unseen because the statistics is so large. And I mentioned previously that to get one particle, you need 1 square kilometer in century to get one particle at these energies. So this works pretty well. And here we start seeing features in the spectrum. Ankle, second knee, the ankle that people call ankle, and then there is a new instep. And so these features are quite well pronounced, so they fit all kinds of broken power laws to it. But my main point is that we know the spectrum very, very well. So how does it compare to TA? And TA, as I mentioned, is a northern sky. And so the Auger measurement is the yellow point, okay? This is the previous one, it's not the latest one. And this is a joint working group. So people try to talk about the systematic uncertainties and to understand what causes the difference. By default, the black and the yellow data points do not agree. Once TA uses a similar reconstruction methodology as Auger, you get the green points here, and then this almost coincides. But then at the highest energies, there was a quite substantial disagreement between Auger and TA. And there is even a declination band when both detectors overlap, so the statistic decreases. But then, even though they use the same declination band, should observe the same sky, there is still some remaining tension between the two experiments. So that could mean that this is some kind of hidden systematic, or it could also mean that north and southern sky are different. So we really need to know. So the next point is the mass composition. And if this would be this, the fluorescence detector, it has a field of view like that, okay? And when air shower enters, sorry, I had to flip this to make the units correct, Air shower enters, so it has to develop the shower maximum within this field of view. So if the maximum was here, okay, usually you have to throw the event away. So to do mass measurement is a completely different kind of statistic, cuts that you have to apply. And the way how it's performed is that if a shower is measured, then the energy is determined calorimetrically, and then it can be binned, okay, into different energy bins. And then this is the distribution of the X-max values, okay? And these different colors are templates inferred from models, okay? And right, and so what this one does is that here you have data of one real event, so this is the slant depth along the shower maximum, and if the event would be iron nucleus, then it would be very narrow, concentrated here, because iron has such a large cross-section, it doesn't fluctuate a lot, so it would be very narrow at this range, but if it would be proton or even photon, we expect much larger fluctuations. Okay? So if one bins the distribution of X-max for a certain energy bin, and one can fit the templates and infer from that with these templates, infer what is the mass. Yeah? And then one has to use some kind of interaction models to get this mass. Okay? So it's a problem, in fact. And these days, usually to determine this X-max, one needs fluorescence detector. However, these days, it's possible to use deep learning on the surface detectors to obtain these green points. And so, because the surface detectors have much larger statistic, because you don't need moonless dark nights, but can measure 100% duty cycle, they can extend the statistic down to 100 EV, and the measurements are kind of consistent. So this is the image. So what happens is that at lower energies, this is 1 EV, okay? At 1 EV, the composition is dominated by protons. Then protons disappear almost entirely. It's helium, and then at high energies, it's nitrogen or oxygen, and no iron is required so far. So it means that the highest energy cosmic rays are just nuclei. The second new feature is that what is observed is that in coincidence with the spectral breaks in the spectrum, the composition also has breaks. Yeah? So this is called elongation rate, and these are protons and iron, and if data closes up to the blue lines, it means it becomes heavier. If it's more to the red, it becomes lighter. So then you have the spectral breaks coinciding with this, and this is new. We have no idea what it means, but we probably have to change the models or refit or ask ourselves what should it mean. Yeah? It could also be a particle physics effect, but it's not clear. And the significance for this is pretty high. Okay, so my last point on the latest data is about the arrival directions. And the only thing that we know for sure, which is because it's more than 5 sigma, is a dipole in the arrival direction. So there is a preferential direction in the sky where more cosmic rays come from, and in the other direction is less. So it looks like this on the sky map. This is in equatorial coordinates. And the dipole changes, in fact, as a function of energy. It changes slightly the position, because if cosmic rays arrive to the galactic halo, depending on their rigidity, they get deflected somewhat differently. So this dipole is like a lensing effect. So the dipole can shift the origin of this, or the axis of this dipole. And in fact, it's consistent. So just from this measurement, we cannot see the difference between that sources, the origin of cosmic rays, that they are uniform at the boundary of the galaxy. Yeah, so this would be the gray bar. And then if they would be coinciding with the mass distribution nearby to MRS, the measured amplitude should be higher, and the data is exactly in between. So we cannot really say that this dipole can discriminate between the origin, but it's an observed feature. Okay, so this is what we know for sure. The rest, now it starts to be more elusive and more speculative, and also more personally biased. And then, so the challenges. And the challenge is that we are trying to do astronomy with charged particles, okay? And how do charged particles behave in magnetic fields is that only a few can escape, and the directional information is completely lost. And this is within the galaxy, and there's about several PeV energies. The other challenge is that on long range, on longer ranges, so this is a plot from Kumiko, Korea, and Angela or Linto, that if we think about sources being at tens or hundreds of megaparsec, there is not just void in between. So particles that are susceptible to magnetic fields, like filaments or different radio galaxies that might magnetize their nearby environment much stronger. Then within our supercluster, do we have any kind of structured magnetic fields? Can we assume it to be random? Are voids really do voids really have these low magnetic fields? And so on longer ranges, we have to take care of extragalactic magnetic fields, which are very purely known. However, we also, within our galaxy, one of the main, even our galaxy is, I think, a very big obstacle for going forward and refining cosmic rays. Why? So imagine you measure a particle at 10 to the 18, 1 eV, okay? And you don't know if it's a proton or it's nitrogen or iron. This is how it is these days. And so at 10 to the 18, if you would try to backtrack, you just follow the directions backward from the Earth, then this is how the trajectories look like. It's completely a mess, okay? At 10 to the 19, you see that, okay, this is 10 eV. Some directions become more straight than others. So towards the galactic center, the deflections are still large, and away from it is actually pretty good. And only at 100 EeV, you get almost straight directions. So this is where we would like to have some astronomy, okay? However, the problem is that we don't know what is the charge of the arrival particles event by event. We only know it on average and not at each energy, but we need rigidity. So because of our position in the galaxy, 8.5 kiloparsecs or away from the center, the deflections that particles experience are anisotropic by design. So we cannot treat all directions equally. The second thing is that because of the missing mass number, you can take the energy and divide it by your favorite number between 1 and 20, to have an idea about the magnetic deflections. So this is a real issue. The problem with this event-by-event composition, I think it's likely solvable in near future. So these neural networks can, in fact, reconstruct X-max, and they could also reconstruct more. However, there is an intrinsic problem with this. So this is bias of the reconstructed X-max compared to the FD and SD, and you see that there is some minus 30 gram shift, so we don't really understand what this neural network see. Likely causes a thing called the muon excess or muon puzzle. So, and this is the expected number of muons, and this is how previous models behaved. So there was a factor 2 or 50% missing number of muons compared to our simulations. Now we have made a new model that should probably solve it, we hope. And if we can have a model that trains the neural networks properly, probably the neural networks can tell us more about the data. So this might be something in the next few years to be solved. The second problem, or third already, is that the galactic magnetic field, even if you would take it into account, is not well known. So Pierre Auger gave a very nice talk a few weeks ago. And this is the update of Jensen-Farrar magnetic field model, which many people use, is very popular. And so this update comes now in 8 different variants, because the data to fit the galactic magnetic field is really like a big cooking thing. Is not, so all of these models have a similar goodness of fit. And this is how they predict the expected deflections for a given rigidity. So just because of the galactic field, magnetic field model, the origin of a particle could be here or there. Okay. So yeah, sometimes it's more aligned, but yeah, it actually doesn't look well. So 10 eV is probably also just too low to remove this effect. So this implication is, the implication is that for all the events that we measure, so this is like TA data from 2015, we have to assume a composition if you want to analyze the origin, and we need to untwist the effect of the galactic magnetic field. And this untwisting of the galactic magnetic field currently happens under two assumptions: the GMF model and an assumed composition. Okay? The GMF model, I think, is maybe on a decade time scale, but the assumed composition is maybe 5 years or so, that we can remove gradually this assumptions. Yeah? So in the end, there are some directions which are very preferential. So this is the TA hotspot. The deflections are very minimal. It's very hard to see, but the circles are actually very, very small. But other directions like here, so this is in galactic coordinates centered on the anticenter, like here, the expected range of variable directions is way too large to have any conclusive thing. So how to identify sources then in this mess of data and model dependencies? And the typical way that has been taken actually by Auger collaboration but also others is to use template fit. So one assumes a catalog of sources, let's say Fermi to FGL catalog or nearby starburst galaxies, and then one needs to assume an isotropic and deflection scale, 25 degrees for example, and then we need to assume that all sources have the same brightness or so, or they scale proportional to X-ray luminosity or gamma ray luminosity or anything, because we don't really know what the sources are, we don't have a good proxy for them. And then you can test the compatibility with the observed cosmic rays. So this is like model input, this is the observation. Yeah? And in fact, people find pretty, there is some compatibility, but not without problems. But are these catalog searches really the right tool? Because you heard me saying 5 times assume, right? So this is an example of why it is actually not, I think. So this is the black dots are the Fermi to FHL catalog within 250 megaparsec. For some this might be just nearby, for others, for us is already very, very far. Yeah? Ultra-energy cosmic ray physics is within 20 megaparsec or 50. Then this is without really fancy modeling, but it doesn't matter. And what we can see if we fit the source associations, and we'll talk more later about how this works, then we can clearly see that Centaurus A, can be associated with many observed cosmic rays by eye. But if you would ask the question about the catalog, so Cen A is in 2FHL, then the resulting source fraction is just 5% or 3. Okay? So if you ask the wrong question, your result is negative, although there can be a very obvious source. Okay? So I think that the simple model-dependent significant result might be a wrong expectation from ultra-energy cosmic rays today. Yeah? We don't know about tomorrow, but today it's definitely true. Yeah? So we need to build correct hypothesis and use as much knowledge, physical knowledge, as we can. So now I come to the opportunities, which talk about exactly this point. So one opportunity is the magic sausage multimessenger physics. Why is it applicable to ultra-energy cosmic rays is that if you have sources that accelerate cosmic rays, they don't accelerate in the void. Okay, so there will be either radiation fields, if these are compact sources, there will be high density photon fields. If these are extended sources or some sort of sources within galaxies, then there will be protons like gas. So the cosmic rays will interact. And the interaction of cosmic rays inevitably, among producing electromagnetic radiation, produces also neutrinos. Yeah? So, and neutrinos don't scatter magnetic fields, they go straight. So if you would identify neutrino sources, you would be identifying also cosmic ray sources. Yeah? So this physics together, like IceCube physics, and maybe some Cherenkov telescope, like ISCT physics, like TV, gamma rays, might be very much connected to cosmic rays, but neutrinos are a smoking gun for cosmic ray interactions. obviously, if you have cosmic rays interacting a lot, producing secondaries, then fewer cosmic rays survive. So neutrino bright sources might be actually cosmic ray dim sources. Okay. But okay, there is this option. So the neutrinos I'm talking about are mostly this high energy parts. So there are many types of neutrinos in the universe, but at high energies we have those which come directly from cosmic ray interactions and those that do not, that come from outside the Earth's atmosphere. And then there is a part at the tip called cosmogenic neutrinos, which really are connected to ultra-energy cosmic rays. And there are very few, there are tons of ideas why neutrinos can be connected to cosmic rays, but none of them really is a smoking gun thing. So this is more on a generic scale. So this, what you see is E-square flux. E-square flux tells you that horizontal lines would correspond to constant luminosity and constant energy density per interval. And this is ultra-energy cosmic rays. These are the observed neutrinos by IceCube, this Fermi gamma ray background. So all of these are more or less within the same ballpark. I showed you that cosmic rays cover many orders of magnitudes, right? So one can, hypothesize that ultra-energy cosmic rays and neutrino sources may be connected. Okay, so the second opportunity is to really use more modeling. And so I choose to discuss a simple model instead of a multi-messenger, multi-collision DRB model to demonstrate how it would work. So let's assume that we have generic accelerator that accelerates particles with a power law and a cutoff. We can simulate in very high detail the transport, and then we can compare the data. Okay? So we assume that the source emits different composition. So these are power laws with a cutoff. This is with E square, so these spectra are harder than E square. And then each of the mass groups can be normalized independently, and there is a cutoff, okay, in the spectrum that depends on the maximal rigidity. So you see that hydrogen, heliums, both they're ordered in energy because an accelerator depends only on energy over charge, yeah? So rigidity dependent evolution. And we need to assume how these accelerators would be filling the space. Okay, so we need a cosmological evolution. And then, in fact, we can take, because most of the cosmic rays slow down quickly, we mostly care about the first redshift of 1 and everything before that. So a model like this, power law with M, with an index M, is actually pretty good to describe various types of sources. And so we can use this model, do a bunch of simulations and fit the 3 parameters of the model, about 10, to the data. Okay, so this is the fit, it works perfectly, it looks very nice, okay? So what do we get? So this is the fit, and the result is that at these energies, so this is 10 eEV, 100, this is 10 eEV. Yeah, this is 100. Right. So the composition is mostly nitrogen, so it coincides with the data here. Yeah, and we can fit the composition. And the resulting parameters are the following. So the maximal rigidity, so we fit a homogeneous and alike distribution of sources, and we can fit very clearly that the maximal rigidity is about few eV. Doesn't need to be excessive. Then what we also fit is that with this model, with this collection of propagation models, is that the evolution is kind of following star formation rate. It's a little bit steeper, but it's fine. So there are some contours that cover more. But then the spectral index is supposed to be very, very hot. Spectral index means that the sources have to inject cosmic rays almost monochromatically. And this is a result in 3D using 2 specific models. However, once we start taking the model uncertainties at Earth into account, like for example, this is the difference between one model to convert X max into mass, and this is a different model. then we get two completely different results. One model tells us, oh yeah, it could be something AGN or starburst-like, yes, star-forming rate-like. However, if we take a different composition model at Earth, it actually suggests that the evolution has to be negative. Yeah, I mean, negative evolution is maybe low luminosity, AGN, and TGEs, things like that. Okay, so, and this tells us that actually the detection is more of a problem rather than building some fancy astrophysical model. We can put more parameters, but we cannot overcome this, at least at the moment. Yeah? But the second thing is we can use this physics to constrain our models better. So from this previous study here, yeah, depending on the source evolution M, we expect additional messengers. The messengers come when cosmic rays interact with CMB. They produce charged pions, they decay to neutrinos, or in muons, and they decay to more neutrinos. Okay, and these neutrinos we call cosmogenic neutrinos because cosmic rays on CMB. And then depending on the source evolution, we get different predictions, yeah, from how the neutrinos spectral visible should be like. And this is the observation of IceCube. So at lower energies, the data from other sources covers most of the expectation, and at high energies, the limits are too far. So there is an order or more magnitude difference. So we are not yet there to be able to dig into this cosmogenic neutrinos as an additional messenger. Okay? The other point that we can use is actually to use directional information. And why does it have to do with energy is the following. So this is the distance at which you inject the cosmic ray. So this is 100 megaparsec. Okay? This is the energy, 10 eV, 1 ZeV. Okay? And if you inject the proton at 1 ZeV at 100 megaparsec, or let's say 200 megaparsec, it would have exactly the same energy as if you would inject a 100 eV proton. So for protons, they lose the initial energy very quickly, and then they become flat. Okay? This is because they also interact with the CMB, and the protons lose energy because they fragment into resonance and so forth. So if you would look for 10 ZeV particles, we can only look within our local neighborhood. Okay? So the sky at extreme energies must be isotropic. So, and this is what happens for nuclei. For nuclei, yeah, we did this study with Noemi Globus and with Roger Bleffold. And what you see here is if you would have an observatory that focuses on nuclei, that measures specifically nuclei, we reject the protons, then and we would look for intermediate masses. The sources would emit intermediate masses. And this is the absorption coefficient. This is 10 megaparsec. So if you would look for nitrogen or extremely high energy nitrogen and above, we could limit our horizon to tens or to few megaparsec. So we can, by choosing the threshold energy and the threshold mass, we can darken the sky. We can increase the contrast of the sources. It must be nearby. However, if we look at present observations of the cosmic rays above 100 eV, this is how it looks like. And data, the squares are from Auger, the circles from TA, and it looks almost isotropic. But the composition measurement tells us it's nitrogen. Isotropic and nitrogen, high energy, doesn't really fit together. Okay? So this is something that is not really explained because most of the highest energy cosmic rays or doublets, they point to nothing. There's nothing. Yeah, this is galactic coordinates, unfortunately. So here's M82. This is the galactic plane. Okay, yeah. So, okay.
What's the localization uncertainty of these events?
1 degree.
1 degree.
I mean, the reconstruction, the reconstructed direction is 1 degree.
Yeah.
But the problem is that there is the deflection, and the deflection depends on rigidity. So if you would know that this is 100 eV and not 100 eV, then actually it would be 1 degree plus minus 2 or 3, right? But since we don't know the mass, it can be also 20 degrees. If it's iron, it will be deflected by 60 degrees. Yeah. So this must have to, I mean, this kind of puzzle does not mean, oh, it's some kind of gazillions decaying. It could simply mean that the composition is rather heavy and consistently heavy. Okay. But it's a kind of a problem with the horizon, because if it's heavy, then they cannot come from two distant sources. Yeah? So we actually don't know exactly how to stick these components together at the moment. Could be transients also. Yeah, that sources were transients, and then or they're coming with the protons, but from high redshift polar, so they got the deflection in the EGMF or in some filaments or whatever. Yeah? So we have no idea. So how to get an idea? And so we are working on building more complex models than compared to what it was. So it's with a bunch of young people. So Francesca is a group leader at Max Planck MPP in Munich. And there's a student, Nadine, and this Kato is kind of my student. And so we are building a more complex model to take the physics into account that's used based on Bayesian hierarchical modeling. And what this model does is that it tries to make the natural use of the horizon. Okay, so for example, if you have a low energy cosmic ray below the threshold for the CMB interaction, then it can cross very large distances. But because it's low energy or low rigidity, it would actually have large deflections. So if you would define some sort of search bubble, it would be this more distant, but also wider. Yeah? So would be kind of, if there would be a source here, well, okay, there could be 50 other sources in this bubble. But it's not very significant. And then for high energies, of course, we expect a narrower range and also a shorter distance. So higher energy or higher rigidity cosmic rays, yeah, would be, we would expect them to be better localized. And the way how it's built is using STEM and the code in Python. So we try to use Anatoli and MCMC. And for example, this simple model is built by Francesca and Modlock, or let's say simplified as an evolution of the effort of many people. So there's quite a thought in this methodology. So this would be S sources. Let's say we have a catalog, 50 sources, and each source would be defined by distance and by direction, omega. And then it would also have a luminosity attached to it and some kind of spectral parameters, let's say a single power. But then we also have n observed cosmic rays at Earth. Let's say we have a sample of 200 cosmic rays, and each of them would have a detected energy and direction with an uncertainty. Okay, so it's not exactly we have like 20% energy uncertainty and maybe 5 degrees directional uncertainty, but that can also be a measure of deflection. Okay, and we can build this model and use hyperparameters. So for example, we can say, well, the extragalactic magnetic field or the source index or the source luminosity must be equal for all sources, and then we want to marginalize over it and give us the association probability. How much can such a source contribute? Like how much, to what extent can a source be associated with the direction and energy observed in the cosmic ray? So currently we use different modeling inputs. So one of these is directed or deflections in the magnetic field. So we use anisotropic search radii, which are implemented as for Mises-Fisher distributions, and so we can use a code called CR proper and Jensen-Farrar magnetic field model to backtrack these and define actually a search radius based on the direction of each cosmic ray. Then for the present we use, for the extragalactic magnetic field, we use a model that simply assumes, okay, it's just a turbulent field with some coherence length, and then we can have a radius expected mean, the deflection radius based on the rigidity, magnetic field value, and so forth. Yeah? All of these and this magnetic field value, for example, something that we fit. Yeah? And then we can infer the source composition, so which, if we want to obtain nitrogen at Earth is observed, what kind of nuclei do we have to inject at the source? So what do you see here is that this is a rigidity of 8 eV, 20 at 75, so the energy increases. And so this is mass group 3, so this is between carbon and sodium or something like that. And then what you can see here is this is the mass number of the injected cosmic ray. So here is iron, and here is beryllium. Okay? And so for lower energies, you can inject the composition at the source, which is very close to what we observe. Okay, so if you want to get carbon, you might need to inject just nitrogen, and the source is 2 megaparsec away and low energy. This is M82, it's actually 3.4 megaparsec. But if you go to high energy, to get one carbon or few carbon nuclei, you actually need to inject something much closer to iron, simply because the nuclei will, within this 3 megaparsec, will disintegrate. Okay. 75. And then we can use the same methodology to assume a spectrum at the source and to account for the disintegration of particles to get the spectra that we expect from particular sources at Earth. Okay, so we can model this depending on the spectral index at the source, which we will fit later in this model. These days, we build a more complicated model. So there are a bunch of so-called hyperparameters like this luminosity and magnetic field value. But so as I said, we have included now the galactic magnetic field effect for each cosmic ray, which is a kind of rigid choice. We don't fit galactic magnetic field parameters, we assume one, and we can repeat this thing. Maybe we can go through the set of 8 models with a new 23 model, but right now we do not. Then we have to assume an arrival composition because we don't have it in the data. However, in the data, if you would have, if you would know not the energy and an assumed composition, but we would know the rigidity of each arrived cosmic ray, this model will not greatly simplify. Okay. So then we use rigidities for the source spectrum, and this is a likelihood that's actually from the old model. We built a nested likelihood, and this likelihood takes into account let's say spatial terms. Yeah? So this is the spatial search gradient, depending on the distance of the source, energy of the particle, and the magnetic field value. This is detection uncertainty. This is the energy loss from the source to the observer. So this gives us the probability that it actually closes this bubble. Okay, this term closes the bubble that I showed in the introduction. And then this gives us also probability for if the source have very steep spectra, alpha, then we don't expect many cosmic rays at very high energy to arrive to us. And this is a Poisson likelihood. Okay? So this now is more complicated using these terms, but the principle is more or less the same. And this is an example result of what we can ask. So in this result, by building a hypothesis, you actually test some sort of theory. You can also test, okay, is M82 expected luminosity proportional to something? Yeah? Here is just simple model. How much does could M82 contribute to the observed events in telescope array, given that the observed composition is helium? This is what TA claims at the moment above that energy which comprises the events. So these sky maps here, they have the dot size is the energy of the particles. So very high energy particles like this one, yeah, it's above 100 eV. Yeah, it cannot be associated to a source because the deflections simply don't fit. Okay, but lower energy particles, the smaller dots, they can still find association, even very distant events, of course with a much smaller probability. And the sum of all the associations, this is called source fraction F. Okay? So what we find is that 70% of the events in TA are compatible with the origin just from M82. One source. Okay, and the others here might come from long distance pileup, maybe there are some other sources, who knows? Maybe they are very heavy, so they would have large deflection angles. However, in this present model, this requires quite large extragalactic magnetic field, about 10 nanogauss. But there is a caveat here that M82 is just 3.2 megaparsec away. So the assumption of having, just the turbulent average magnetic deflections on a scale of 3.2 megaparsec, with a coherence length of just 1 megaparsec, is probably not accurate enough. Yeah? So there must be some directionality involved. And what we also find, so for example here, this is alpha B, the spectral index of the background, the remaining event. And this is spectral index alpha S, the source spectral index. We have only one source, so we fit the spectral index of M82 essentially. It's required to be hard, between 1 and 2, which is expected. This is completely in line with what other methodologies return for, as also the study before I showed that harder spectral indices are always required to fit ultraviolet cosmic ray observations with nuclei. And also the luminosity must be pretty high. So this has to be about 10 to the 45 ergs per second. Okay, so if you would get now from a different source, from some model, you would get a different prior on the luminosity. For example, okay, if we associate it not with M82 but it's an A, the jet, and then someone would make a model and the model would say, well, the jet can emit only this, then we would plug it into the analysis and it would give us all the other constraints. Yeah? So this kind of method, the machine, we can include theory now, step by step, or different hypotheses using priors or using partial model replacements and so forth. Yeah? So we are building this kind of playground and we are looking forward to actually apply it to more data and different hypotheses. Okay, so to conclude, I could cover only a small biased fraction of what ultraviolet cosmic ray physicists do. And the low-hanging fruit have been picked many years ago, because it's about 100 years of cosmic ray studies. People have been smart always. Modern data quality is actually very, very good. We have enough statistics, so this cosmic ray physicist whining that, oh, we don't have enough statistics. I think we do have enough statistics, in particular for these Bayesian methods. They become more troublesome if we would have too much statistics, actually. The crucial ingredients to pick the high-hanging fruits, and this is now the identification of sources, is event-by-event composition. This is very, very clear, I think, to everybody in the field. And then this can allow us to tackle the impact of magnetic fields properly, without saying assume, that would give us, okay, this is a precision, and under these models, we would have these intervals that we can sample with. There are plenty of methods and tools developed for propagation, for magnetic deflection, even for not detailed implementation and measurement uncertainties. Then new methods like the Hamiltonian stuff allows us to confidently marginalize over hundreds of parameters. If the model behaves well, and it takes effort to make it behave well, then it can actually swallow hundreds of parameters and can marginalize over many of these. And it's actually working pretty interesting, and it works, it's there. And the next steps is to focus on choice of the priors. So as with every Bayesian analysis, this is quite crucial, which direction it takes. And also include more sophisticated source propagation models, so there are plenty to choose from, also within my own toolbox. And then determine which hypothesis to test. And this is the theory is entering, because it's just going beyond catalog searches and the circle on the sky. So here we can actually ask quite detailed questions, also about galactic, extragalactic magnetic fields. What we crucially need is composition data from TA. And I'm putting manpower in it. Anton, he is the person of choice to solve the problem for us. To start a data analysis on machine learning, identification of mass in TA, because this is completely absent right now. And all of this, I think, goes into the direction to determine what do we actually, where we want to go with ultraviolet cosmic rays, and what can we do with a new machine. And for that machine, we need to define the science goals and the capabilities and what are we going to do in the next decades. Yeah. Thank you.
Questions for Anatoli?
Sorry, what only means part. I wonder what's the reason that you choose M82 as the example to sort of reconstruct?
It's the closest one. I mean, in this area, so this is centered to galactic anti-center, and here is just a bunch of dwarfs. Like within 10 megaparsec, there is nothing else. Yeah, M82 is the closest one. Yeah, and I mean we have catalog searches, but in fact if you have a catalog, then you need to assume something about the distribution of cosmic ray luminosities. Okay, so if you assume similar luminosities, then the closest one will simply outshine the others. Yeah, I mean we have also catalog searches, but this is like one example. For Auger, clearly the M82 equivalent would be Sen A because it's directly within the exposure. Sen A is here, so it's not within the exposure of TA. Yeah.
So isn't that also because one of the theory for cosmic ray production is related to supernova, starburst, and so on? Is that?
Yeah, I think yes. This is a long story, but some people. I mean, there is a evidence for about 8% of cosmic ray events to come from starburst galaxies. Using circular search radii, I think this analysis that I showed, this one, this assumes a catalog of nearby starburst galaxies. Here I have M82, NGC 253, and so forth. However, I don't know of any very convincing model that would accelerate 100 EV by superwaves or something like that. Yeah. So it could be something related to starburst, but this could also be just coincidence.
Other questions?
I am interested in accelerator cosmic rays in M82. So if I am correct, the M82 does not have a AGN or something like that. So,
What? No, yeah, not really. Yeah.
So I am wondering what is the accelerator of the cosmic ray in M82? Do you have any idea?
I don't know. I mean, I think Nagataki-san is probably the one to ask. He likes M82 to be the source. But in my opinion, I don't know what. I mean, okay, let's put it this way. If it's a starburst galaxy in a let's say later stage of a starburst phase, okay, then and if the sources would be transients like GRBs, yeah, then you would expect, yeah, in a later stage, you would expect that, or let's say if there would be pulsars with some inductive acceleration or any kind of exotic thing, to accelerate ultra-energy cosmic rays, you need actually lower density. Yeah, if you have very high density, be it photons or matter around the source, you don't get, the turns or even inductive acceleration would needs a large termination radius in pulsars, for example. So in a underdense bubble, in a post-starburst or like late starburst phase, you might have actually these conditions, yeah, which would be almost void, yeah, large termination shocks of pulsars, and then you would be able to accelerate. So it could be something related to the starburst phase. But I wouldn't say that the starburst galaxy by design, has something to, like, that it's the galaxy, it's something inside the galaxy. Yeah.
So I'd like to ask about the event-by-event composition.
Yeah.
So are you planning to use the exact same sets of observable?
No.
No. Is there new available information?
Yeah. So I mean, there is effort by Auger. Yeah. So for example, this is a waveform in the water Cherenkov detector. So how do you determine composition event by event? In principle, you need to measure separately electron and muon number. Okay. In a water Cherenkov detector, particularly if you have a scintillator on top, yeah, you can measure the electromagnetic component with the scintillator, and then with the water Cherenkov, you would measure electromagnetic plus muonic component, because the response is different of a muon, yeah? And then you could kind of unfold this and get the separate measurement. In a purely scintillator-based experiment, this method would be not possible. So this is a water Cherenkov, the photons, muons here, electrons, yeah, and some late pulses like this is attributed to photons, but muons here are almost covered. So there is like this small peak maybe or something like that. And if you go further away from the shower core, then you expect less and less electrons. You expect more signal from muons. Yeah? So in the end, we have to really study, like define new parameters that are not, human identified parameters. Yeah, to like use random forests to derive new parameters and then use them to train machine learning algorithms.
Yeah, the new feature is very important, not just the
Yeah, absolutely, yes. Yeah.
Thanks. Do we have other questions, Anatoli? Okay, if not, yes, go ahead.
So, as I remember, several years ago, there is some tension on the composition between the TA and the Pierre Auger telescope.
Yeah.
Now, do you expect still tension is or
Yeah, I think the tension mostly is discussed away. I mean, there was again an incident at the conference where the speaker from TA said, "Oh, it's just a K kind of, it's protons." Yeah, but in the end, I think the data, like everything that comes out from the joint working group and from this cross, so TA and Auger exchange detectors, for example, or exchange simulation software, exchange reconstruction technique, and whenever they do this, they find very consistent results. It looks like in TA the mass composition might be a little bit lighter than Auger. There is also this spectral feature. This one, yeah, that doesn't go away. Yeah, so that also might actually, we don't know. Maybe this is some kind of protons or helium excess. Yeah, so it would make the composition generally lighter in TA. Yeah, but I think there is no, like if you would use the same models, it looks completely consistent. Yeah, so I wouldn't say there is any tension left.
Okay. Any last questions or comment? Okay. If not, let's thank Anatoli again.